All right, I'm going to go ahead and get started. Thank you for coming to the session. My name is Jonathan Balkind. I am a new assistant professor at the University of California, Santa Barbara. I'm a professor of computer science, and in particular, computer architecture. I'm going to be presenting today on an aspect of our system, OpenPiton, which we have been developing throughout my PhD at Princeton. I was the lead architect of OpenPiton over a period of about 6 years. And we started on the project back in 2013. So there've been a large number of people who worked on this. And so this is a big collaboration presenting work done by a lot of people. And OpenPiton is a many-core research platform. And underlying OpenPiton is a scalable cache-coherent memory system that we call PMesh. And so what I'm going to be talking about today is PMesh itself and how to use PMesh to build cache-coherent heterogeneous ISA processors. So, clicker isn't working just yet. So PMesh, as I said, is the cache-coherent system which underlies OpenPiton. And OpenPiton is a system for building many core SoCs. It started out as a platform to enable our research ideas, and it's kind of grown and become more mature and usable. And so, now if you're interested in building a coherent SoC, then you might be interested in using PMesh as a coherent system for that. Now, you'll notice I mentioned many core rather than multi-core. Our research in general has focused on extreme scalability. And so we have designed the PMesh coherent system to have scalability in addressing up to 500 million cores. You might never want to build that system, but the idea is that this enables us to test out the problems that come when you try to scale to very large scale. And the picture on the right here is kind of like a PMesh system, like a system with some cores and so on. And the orange box is the PMesh part. And so you've got kind of some layers of cache to provide you with your coherence. And we have 3 physical networks on chip, which enable kind of deadlock freedom and data movement efficiently. The idea is that you can kind of connect a variety of different things and build a really large system around this. And so you'll notice these kind of red boxes at the bottom, the different cores that can connect into the system. And the way that we connect these is using an interface that we call the transaction response interface. And the idea here is that we can be kind of configurable and connect new types of cores that we've never seen before by building this interface. So far, we've connected more than 10 different cores with 5 different ISAs into PMesh. And we specifically have support for heterogeneous ISA systems that I'll be talking about today. So you can actually have the cores that I note here living together in a single system. On top of that, we support a variety of different peripherals and accelerators using standard interfaces that you can connect into PMesh as well. So why would you want to build heterogeneous ISA systems at all? The norm is that you build a chip with multiple cores and those have a single ISA, a single microarchitecture. And that's easy to do in some sense. You can stamp down the same block multiple times in your chip, and you know the behaviors, and it's easier to validate. But within the last roughly 10 years, it's become more common to build single ISA heterogeneous microarchitecture processors. So things like ARM's Big Little, where you can kind of extend your DVFS curve that you see on the right here to get more performance or power benefits based on what your application in particular needs. So if at the moment you really care about performance, you can get a crank up, move to the bigger core, move your DVFS all the way up. And if you want to save power, you can move down to the smaller cores and take advantage of those heterogeneous microarchitectures. But the big question is, what about the ISA? Are there particular features to particular ISAs which have benefits that we could also take advantage of? We're in the post-mirror world. We want to try and get, the small benefits that we can get where we can get them. And so there's been prior work in the architecture realm, which has shown, in particular, so this chart here is from Ashish Venkat and Dean Tulson, which has shown that you can get performance and energy efficiency benefits by migrating your application between cores of different ISAs. So it turns out that applications and phases of applications have affinities to particular ISAs. And so if you care about, getting your performance, then you will want to have your application run on a particular ISA for, a certain period of time. So you can see this chart on the right here showing which ISA will you get the maximum performance for which proportion of the execution time of the application. And then they also said, well, it turns out that these differ depending on your goal. So if you care a lot about energy efficiency, then the ISAs that you want to make use of might be different from if you care about performance. And you can imagine that there's particular ISAs that have high code density, or there's particular ISAs that have vector extensions, different features that would be advantageous for different applications. And we want to try and take advantage of that and move our applications around for the best performance and energy efficiency. Now, the issue here is that in terms of the architecture research, the work was done in simulation, because there isn't actually any hardware out there that can give you kind of a fine-grained, high performance, low latency, cache coherent fabric for cores of different ISAs. And so instead, systems people saw these kinds of results and said, why don't we try and build heterogeneous ISA operating systems with the hardware that we do have available? And so there's a couple of different examples here. One of them is Popcorn Linux. And in general, that's been kind of, you take a big Xeon server and you plug in an ARM PCIe card, and then you try and build an operating system that will let you transition applications between the two ISAs using PCIe message passing and software-based coherence. Another one is K2, which can run on ARM and Thumb, and it would also use software coherence. And so these are relatively heavyweight mechanisms for providing coherence to your application. We kind of asked, is there a way that we could build a cache coherent heterogeneous ISA system so that we could realize the architectural benefits and improve the OSs to be able to kind of have this capability so that we could actually eke the most gains that we can out of the hardware that we have available to us. And so we built a system that we call BYOC, that's short for bring your own core, because that's what we want people to do. And this was really kind of like an extension to OpenPiton, an improvement to PMesh, kind of new version of PMesh in some sense. And the reason that you might want to build this in terms of kind of an end user's needs are that you might have a particular application or a particular design need that can only be met if you bring together cores of different ISAs. So maybe you are in need of the most performance you can get, and you want to really squeeze that, or the energy efficiency. But there are other needs. So maybe you are in aerospace, for example, and you need to make use of an application which is high assurance, it's been validated for particular purposes, but you want to have some other cores that do some other function. Can you bring those together? Or maybe you want to save as much money as possible, and you want to you have particular cores available to you. You want to exploit the ones that you have available as best you can. And so the idea here is that we can build a system where you can bring together all those cores all together at once and have them coexist. And previously there was kind of only the capability to do this for cores of a single ISA or a single microarchitecture. It's much easier for you to just kind of stamp out many of the same core, many cores of the same ISA. But we were building an open source cache coherent memory system, PMesh, explicitly for heterogeneous ISA. On top of this, we built this new core interface to cache coherence we call it Transaction Response Interface, or TREE. And we actually built what we believe is the world's first open source general purpose heterogeneous ISA processor, and that's called Piton. And I'll talk a bit more about that shortly. So the system that we were building all this on top of is called OpenPiton. And OpenPiton is an open source manycore research platform. It's been open source since 2015. We've been doing development for about 7 years at this point. And the idea is that we wanted to test out certain research ideas at Princeton. And once we got to a certain point, we said, we have a great system that other people could use. Why don't we make this available? We validated it at this point, that we did the release, we taped out the real chip. And so, we actually have like a highly functioning system. The platform itself is written in Verilog RTL, so you don't need to learn a new hardware description language to go make use of it. And as I mentioned, the coherence system is designed to scale to extreme scale. We tried to provide a lot of configurability, both in the cores that we provide and in the uncore, so that you can find the right design point for your idea and test it out, at the design point that you care about, or just find, the one that's going to be optimal for the metrics that you care about. We provide a thorough validation suite so that you can, go and modify PMesh and then check that you didn't break anything. And we're making active use of that just now as we work on our new chips. And we also provide simulation with all of the major Verilog simulators, essentially. And we have the companies who build these tools coming along and using the OpenPiton RTL to test their tools and to test their tools at scale, because there aren't a lot of other examples of, really highly scalable open source RTL designs out there. And so, people are coming along and adding support for their tools into the platform because they want to test them out that way. We also provide a synthesis and backend flow based on the Piton chip that we taped out in IBM 32 nanometer process back in 2015. which is a relatively unique thing to provide. And that chip itself, as I mentioned, has been verified. We have that real chip in the lab, and it works. We did a very thorough power and energy characterization that was published in HPCA 2018. And so you can get really good ground truth about the design that you're trying to use in order to understand the power and energy behavior it should have. We also provide the same platform on FPGA, and in both ASIC and FPGA, we can run full stack multi-user Debian Linux, and that's on multiple ISAs too. So OpenPiton itself, the PMesh system started out just with the OpenSPARCv9 core. And as you may know, Spark isn't in active development anymore, and we were interested in branching out and looking at this heterogeneous ISA problem. But the system we designed had kind of a number of Spark-specific specializations. It had certain kind of core-specific, microarchitecture-specific specializations. And so the big question was, how do we connect other cores and how do we support other ISAs in a way that's flexible and allows kind of anybody to bring any cores? Now, when we started this project, when we started OpenPiton as a project, we only really had the cores in the first 2 columns available to us, open source that we could potentially work from. And based on our needs, there was only really one that kind of met what we wanted. But today there are far more cores, and so we really want to take advantage of this reemergence of open source hardware. I mean, we're kind of part of this vanguard that's pushing this, and be able to support as many cores as we can and try and build something that is usable by many people and is very flexible. And so there were several ways that we could conceive of connecting new cores, and they have different trade-offs. And the really important thing was minimizing this effort, right? So you can come along, modify your core minimally in order to connect it to the system. So the first option we had, we call option A, is that we would provide 3 levels of cache, and the end user would kind of connect their core to an L1 cache that we provide. Now, this isn't necessarily a very desirable design point in terms of cache coherent memory system to provide, and that the L1 is generally very tightly coupled with the core microarchitecture. It's typed the ISA specifically. It's a very high performance point. You want to have low latency. You want to have high bandwidth to your L1, and so it would be difficult to build something like this. So we then considered an option B. In option B, we would provide just the last level of cache. The end user would come along and they would implement the rest of the cache coherence protocol to talk to the last level cache and keep things coherent. The problem here is that cache coherence protocols are notoriously hard to validate. The PMesh coherence protocol has 30-something different message types. It'd be highly likely that the end user would come along and implement their re-implementation and have it be subtly incompatible with the ones provided by other cores. And so we were not really very excited about this option either. So we settled on option C. Option C is that we provide a last level cache and a layer of private cache, and we try to encapsulate as much of the cache coherence protocol as possible. Then the end user comes along with their existing core and might make modifications to their L1 to speak to our layer of private cache. But that's after the L1, and so it's a kind of lower performance, lower bandwidth and latency requirement than the option A. But also we have the more thorough validation opportunity of option B over option B. So we defined this new interface, the black dotted line that you can see here, called the transaction response interface, or tree. And the idea is that tree should be simple. You can see there's a relatively small number of message types that are needed to implement tree. It's extensible. You can choose which ones you want to implement. So you can start out with just kind of 4 different message types to some loads and stores, even fetch your instructions using the load store interface. And it's low overhead in terms of number of wires needed to kind of connect up, the complexity of the state machine, that sort of thing. And so to say a little bit more about that, I'll show you some of the cores that we've connected and the different subsets that we implemented. So the OpenSPARCv9, that was the core that came with OpenPiton, and so the first thing we were doing was trying to bring this forward, advance this to the new interface, and so it supports all the subsets. Then we worked with ETH Zurich to connect to the Ariane core. I'll talk a little bit more about that in a moment, and they can have kind of SMP Linux booting in the system. Working with the University of Washington team, the Bespoke Silicon Group, to develop Black Parrot. So they've been developing Black Parrot for the last couple of years. And they had a couple of master students come and work for a quarter, so about 10 weeks, 11 weeks. And they were able, within that time, to connect the core, implement all the subsets, and get it to run many core simulations. And so, this is where we're at the point now of trying to do Linux bring up on this is very kind of high productivity. We have other cores that implement fewer subsets. So, there's the P-core B32 core. That was the first core that we connected other than the Spark core. We have the AO486 is a re-implementation of Intel's 486SX. from back in the 80s, and we have other options here. In particular, we have microwatts. So this is the first OpenPOWER core that we've tried to connect so far. And so far, we implement the instruction subset. So you can actually fetch and execute instructions out of the iCache via tree, and the load store subset as well. So you can perform loads and stores, although that part needs some work. Now, to support more, you are going to want to implement the rest of the subsets, right? So just now you could go and run some simple applications, but if you want to have multi-core, you want to be able to put an OS, you're going to have to go and implement more stuff there. But I was able to do this in the very short period of weeks to kind of get the initial support, and I've never touched VHDL before. So the first proof of concept that we built, I mentioned, is called JuxtaPiton. And JuxtaPiton is, we believe, the world's first open source general purpose heterogeneous ISA processor. So the idea here is that we bring together an application class core that can boot a real operating system, in our case Linux, with a kind of microcontroller class core, and have them coherently share memory under the hood. So we actually boot Linux on the Spark core, and we can transparently offload binaries of a completely different ISA that the main core really knows nothing about to the microcontroller core. And so it can also even have syscalls proxied back to the T1 core to be able to reach its goals. So this is a really tantalizing hint at what we would be enabling, right? If we have heterogeneous ISA, we can say I have application needs that mean that I want to run my application on a different ISA, or I know that I will get better energy efficiency. Let me transition this application onto the core where I'll get the energy efficiency. And the core doesn't even need to have a full operating system to do that. It can still give you the capabilities that you need. And so all of this is open source today as part of OpenPiton. You can go and just pass some extra flags to the tools and generate a version of JuxtaPiton that meets your wants or desires. And so at this point, we wanted to say, okay, what if we could go further? Can we connect other cores? Can we go to more capability, right? Can we start to look at having operating systems of both cores and do something more interesting? And so, this was during my PhD at Princeton. I set up a collaboration with ETH Zurich. They have their Ariane core. And we wanted to connect together the Ariane core with PMesh, with OpenPiton, and kind of build a new permissively licensed manycore research platform. Now, because we're bringing together kind of maturing, sensible designs, you would hope that we would be able to do this very quickly. In general, that isn't really an assumption that we would have had before we started this project, right? These are complex systems. We're talking about cache coherence. We're talking about running full OS. But it turns out that with the way that we cut the system, we built this tree interface. We were actually able to work very productively and exploit the thorough validation of PMesh in terms of its ISA-agnostic functionality. And this is a core of realistic complexity. So we were able to come together within 6 months. We were booting SMP Linux. It was even last time just to get kind of many core simulations running. And so to do this, I'll say a little bit about the design itself. So I showed you the tile before of OpenPiton. This is a slightly different rendering of it. We have the Ariane core on the left, and we have the PMesh part on the right. And so we had to make some modifications, of course, to do this. And so on the Ariane side, they kind of built a new right-through cache subsystem with the invalidation so they could do the multi-core and the speaking tree to RL 1.5 cache. On our side, we were adding the new capabilities to say, okay, let's support other ISAs. And so we needed to support load reserve store conditional atomics. Those are used in RISC-V, they're used in OpenPOWER, they're used in OpenRISC, they're used in a variety of different ISAs, and that's something that we didn't have. On top of that, we wanted the fetch and up atomics, and so we implemented those in our L2 cache as well, because those were demanded by the ISA. At the platform level, there were also some further modifications. And this is something to think about. If you want to bring your core and plug it in, this is going to tell you in general a little bit about what you might need to think about. So one of the things that we did was we auto-generate the boot ROM based on the configuration of the system that we built. And so if you have this particular UART, you have this number of cores, we specify all that and build the device tree into the boot ROM. So you can then take the same Linux image and boot it across multiple different configurations of the system, and it will still work. There's things like debug and interrupt controllers. Once somebody has connected one core of a particular ISA and platform, other people can exploit this. So when we brought along the Black Parrot core, it was able to exploit the boot ROM and the interrupt controllers from our connection of Ariane, and that was able to save us a lot of time in terms of trying to transduce between different protocols, or trying to make things work in ways that they hadn't before. So from this, we were able to get back to our goal of building, complex heterogeneous ISA SoCs. And so the next one that we built had a T1 and an Ariane core, and both of them are application class cores that can be a real operating system. And under the hood, they have fully hardware coherent shared memory, including all the ISA specific atomics. And so the cores each boot an independent Linux kernel, one for each ISA, and then user mode applications on top can share memory across the two cores and the two ISAs, and they don't even necessarily need to have any idea that the other person that they're synchronizing with isn't running the same ISA they are. So we can use the ISA-specific atomics, and those will work correctly even when they're mixed together. So you might use a load reserve store conditional on one side, but use a compare and swap on the other. And one of the cool things here is that this means that you could even have cores using atomics beyond what their ISA is specified to support, and so that you could enhance the core to have a broader ISA potential. Now, because we care a lot about open source, we actually did a full artifact evaluation for this for a paper in ASWAS 2020. So you can go online and grab the artifact, reproduce what we did, and the prototype code is all available on GitHub as well, so you can rebuild it in whatever way you want. And so the next thing I'm going to show you is a quick video of the kind of proof of concept demo that we built. So here we are going to boot Linux on both of the cores, and on the left is the T1, on the right is Ariane. And the T1 is kind of in charge. It's going to map a contiguous region of physical memory and then create virtual memory mappings for that region. That's going to be the first application that gets run. And there isn't really anything special there. It's just going to kind of mmap, get a contiguous region from the kernel and then mmap it. On the right, the Ariane core is then going to run its application. It's going to read from a shared location what the base pointer of that contiguous region is, and then it's going to build its own virtual memory mappings for the same region. Then the two cores are going to run kind of a simple token passing application through a queue in the shared memory. And we have two versions. The one we're going to show here uses the atomics of the two ISAs, but you can also do it just using regular loads and stores. And so we kind of are able to measure out what the round trip latency is. We have other experiments where we measure the throughput. And we can see this is very low latency especially compared to something like, PCIe message passing or, software controlled coherence. And so we're able to realize kind of the benefits that the architects had wanted, but the hardware wasn't there for. And so, OS people could go from here and start to build more complex, more interesting operating systems on top that can actually take advantage of this, low latency hardware supported cache coherence. So another system that we built was I worked with the developers at Xilinx of a system called libsystemc TLM SoC to connect QEMU to PMesh. So their system can connect QEMU to RTL simulation, and the QEMU will do loads and stores into the RTL simulation, and you can handle those how you want. So we had an L1 cache, we transduced that to tree, and then we had that able to speak to a coherent PMesh fabric. And so then there's a lot of potential here. Right? You could bring together cores of ISAs that don't have open source implementations. You could bring together cores, kind of QEMU with simulated cores of the same ISA, but kind of functionally different microarchitectures in some conceptual sense. And then build some really interesting systems. Maybe you have implementation of an ISA and you're building a new core and you want to kind of be able to work alongside an existing core and see what the behavior should be. So this is also a really interesting setup that we built. So really the goal overall is to have OpenPiton, or kind of the extension BYOC, give the features of PMesh to all cores regardless of their ISA. We want to provide a set of features that is rich and sufficient for a variety of different ISAs and microarchitectures, and have that be kind of agnostic to the core. And so on top of what I've already shown, we also built a prototype of an ISA-agnostic hardware transactional memory system inside PMesh. So you can imagine if you don't want to have to add a lot of support in your core for transactional memory, then you could take advantage of one that we build into PMesh, or you could, be able to enhance your ISA to support transactional memory if it doesn't already. There are other things that we're still working on. So we have a couple of tape outs that are coming soon. In particular, we have a tape out next month that's going to have a really kind of complex, interesting, heterogeneous SoC that we'll be happy to talk about in the future. But other improvements, I'm really interested in adding full system microwatt support for the new other OpenPOWER cores, trying to build distributed interrupt controllers that can scale to the scale that we care about, with the potential to be able to have a kind of platform that could be common across multiple ISAs. More center bridges, so we can connect more different types of accelerators, so we can talk to other kind of coherent fabrics, that sort of thing. And then also trying to support things like core clusters per tile, so that you could, if you have a design point that cares about sharing that local cache that we provide, then you would be able to build that kind of thing as well. And so really you're just trying to build a complex heterogeneous SOC environment where other people can bring their cores and plug them in, or they can take the coherent system PMesh that we provide and connect their own cores. And so maybe you don't care about the heterogeneous ISA features themselves, but you want something's well validated, and having been validated across multiple ISAs, will help demonstrate that. So with that, I'm going to stop here, and I'm happy to take any questions that you in the audience might have. Thank you for listening.